This episode is brought to you by Cisco Educational Premium. Did you know that the general theory of relativity is also known as Einstein field equations? These equations relate the geometry of spacetime to distribution of matter within it. These equations are analogous to Maxwell's equations of electromagnetism. Only here we are dealing with spacetime geometry. Einstein's field equations are partial differential equations. They can be written in the form G sub uv plus G, a Hill symbol thing, G uv is equivalent to K T sub mu v, where G mu v is Einstein tensor, G mu v is a metric tensor, T mu v is a stress energy tensor, and that Hill symbol is the cosmological constant, and K is the Einstein gravitational constant. Einstein field equations can be defined as G mu v is equivalent to R mu v minus half R G mu v. The term R mu v is the Ricci curvature tensor, and R is the scalar curvature. It is a second degree tensor depending only on the metric tensor and its first and second derivatives. Einstein gravitational constant can be expressed as a function of gravity. In this form, K will be equivalent to 8 pi g on c raised to 4, which is roughly equivalent to 2.077 times 10 raised to negative 43 n raised to negative 1, where we have a g to be the Newtonian constant of gravitation, and c is the speed of light in a vacuum. Einstein field equations can be expressed as a function of time. Here it is expressed as R mu v minus half R g mu v plus lambda g mu v is equivalent to kt mu v. The expression on the left represents curvature of spacetime, and each term here has units of length squared. Length 1 has units of 1 on length square. The right side represents the stress energy momentum content of spacetime. Einstein field equations work well with geodesic equation. These equations together are able to tell us how freely falling matter moves through spacetime. Matter curves spacetime, and spacetime tells matter how to move. Cosmological constant was initially absent in Einstein field equations. Einstein later added it to his original version of EFT to allow for a universe that is static. This was, however, unsuccessful as evidenced by astronomical observations. Yet the equations still work well with it. This shows that at times in life we need mistakes and imperfections to be perfect. Solutions of Einstein field equations are metrics of spacetime. These metrics describe the structure of spacetime surrounding the inertial motion of objects in the spacetime. This is successful although the equations cannot always be completely solved since they are nonlinear. We can have exact solutions for Einstein field equations. These cases are quite surprising, and study on these exact solutions to find out what they mean is one of the current activities of cosmology. This study has even led to prediction of black holes and to different models of evolution of the universe. Einstein field equations were first published in 1915. These equations were published by Albert Einstein himself in his 1915 paper. Einstein came up with them by first obtaining field equations in a vacuum, in a rather geometric fashion. After this, he obtained field equations in the presence of matter from the field equations in a vacuum.